Welcome to FYI, the For-Your Innovation podcast. This show offers an intellectual discussion on technologically enabled disruption, because investing in innovation starts with understanding it. To learn more, visit arc-invest.com.
ARK Invest is a registered investment advisor focused on investing in disruptive innovation. This podcast is for informational purposes only and should not be relied upon as a basis for investment decisions. It does not constitute, either explicitly or implicitly, any provision of services or products by ARK. All statements made regarding companies or securities are strictly beliefs and points of view held by ARK or podcast guests and are not endorsements or recommendations by ARK to buy, sell, or hold any security. Clients of ARK Investment Management may maintain positions in the securities discussed in this podcast.
Hello. Welcome to FYI, the For Your Innovation podcast. I'm Brett Winton from ARK Invest. With me today, I have Nemo, our Multiomics analyst extraordinaire. Hi, Nemo. How are you?
Great.
Great. We have a great show for you today. Today, we're talking to Gilad Almogy. He is the CEO of Ultima Genomics. They are producing, I think, the least expensive genome in the world. You can buy an Ultima machine, stick it on your shelf, and spit out whole human genomes at a low cost of $80 per genome. And they begin to make commercial inroads and are, I assume, growing quite quickly. Nemo, why do we sequence DNA? What are these end markets that they're targeting? How should we think about the space?
The first human genome was sequenced 2003. It was a 15 or more years project. And that was just basically, learning how to actually do it. And then we realized, there is so much information there that one genome obviously is not going to be enough. And so when we think today, the space has spent a lot of time in academia and for kind of different research purposes. And we are seeing today kind of three big kind of buckets of the DNA sequencing, even though it's kind of used across the biology in the research in kind of for every different kind of subsector, basically. But three main ones that we see is the population level sequencing. So UK Biobank was one of the first kind of big projects where they did 500,000 whole genomes. Now we have all of us, which is 10 million genomes in US. Then we have a 1 million genomes veteran program. I think China was doing 20 or 25 million genomes program. And this is the kind of the biggest kind of bucket, and it's growing the biggest one, the fastest, because we could see even today, just Canada announced that they're going to do 100,000 genomes project. So every country is going to be doing this. And when we did this UK Biobank 500,000, we then just realized, that's just the start. That's definitely not enough, again, for us to understand everything. And so population genomics is the kind of biggest kind of layer, because I think where it is going to move to eventually that everyone gets their genome sequence maybe on an annual basis. The second kind of piece, this is much more in academia as well, but now going to a drug discovery, is the single cell genomic space, where you have single cell RNA sequencing and spatial. And so projects like building the virtual cell, building the human cell atlas are trying to kind of sequence many, many cells. Humans have between 38 to 42 trillion cells. So, and cells, are much more complex than the genome, let's say like that, what we are reading with the single cell genomics. So there we could see billions of cells experiments done very easily and kind of going to trillions. And then the third bucket is the diagnostics, where we have seen the kind of liquid biopsy, especially the MRD space, growing really, really fast, where we are, again, also using the sequencing. And here, why this is also very important, because here we see, every sequencing is a snapshot in a time, but biology happens over the time. So one snapshot, especially in the cancer application, is not enough, and we need this like kind of longitudinal sampling. So that's the kind of third bucket where I see the biggest application.
Yeah. So the population scale genomics is basically like, I take the recipe for somebody's body and I see what their health outcomes are. And so then I can be like, oh, it turns out that mutation was important because it increases your risk for heart disease. And so then maybe you need to get on drugs to manage heart disease conditions more aggressively if you happen to have that set of mutations. Then on the single cell space, it's kind of the, taking a smoothie of all of the DNA in your body and like reading it out doesn't get you the particular information that matters for how kind of DNA expresses itself in your kidney. And so doing single cell sequencing is to understand how cells operate in the different systems they are in the body. So it's particularly important, for example, for drug development. If you're trying to, target a drug at kidney disease, you need to have an idea of how that drug entering the cell is going to cause the cell to change its expression. And then the MRD space, which is growing, quite quickly. This is the idea that, for the vast majority of cancers today, somebody has a cancer, hopefully they get into remission, and the standard of care is like, okay, come back in a year and a half and we'll take a picture of you and see if we can see the cancer growing anywhere. Now, the picture is an X-ray or an MRI. And that's an extraordinarily crude way to find if the cancer has recurred. In fact, because once you've seen it on the picture, that means it's really grown. And these cancer cells are sloughing off DNA into your bloodstream as they die. So if you can create a test that actually detects the cancer in the bloodstream, which they've done, you can detect the cancer months earlier than it shows up in the picture. So you can begin to prophylactically treat it before it gets big enough to see, which seems obviously like the direction to go. Part of the challenge is you have to do lots of sequencing, which if you're at $1,000 per genome is very expensive. And Ultima, is trying to penetrate this market with an $80 sequencer, as Gilad will discuss. So it's an exciting space. I think one of the things that I find fascinating about it is that there are so many different kind of like ways to try to peel this apple. There's PacBio does long read, Oxford Nanopore kind of like drops its molecules through a little like hole, and this is what Roche is trying to do and read them as they're dropping through the hole. Illumina, chops them up and sends them through little like glass channels. And then what does Ultima do?
Yeah, so Ultima is kind of using similar approach as Illumina, but instead of having the kind of small wells and channels, they're using much bigger kind of flow cell or surface on which they have the bead surfaces, and they are just amplifying it. And in addition, Illumina basically makes many mini reactions which are very enzymatically expensive. Ultima, in addition to kind of having a much bigger surface, which is very, very cheap, and you don't have to have these kind of mini wells, it's also kind of approaching this different way in reading this the DNA in terms of that you don't need to use so much enzyme as actually Illumina is doing. So basically, they are reinventing Illumina approach, but actually being much smarter in actually how can you be more efficient by having the bigger surface and then kind of using much less reagents, and then also increasing the accuracy because they use kind of different kind of camera system.
Yes, and so you'll hear Gilad describe it in even more detail and find out, does he really plan to head towards a $10 genome? The answer is yes. And kind of where is the space moving, particularly as it intersects with AI and the acceleration in AI. So hope you enjoy the conversation, and thank you for joining the pod. Hello, welcome to FYI. Gilad, welcome. So you were at Applied Materials, you were a solar entrepreneur, and then you ended up making a radically inexpensive instrument for sequencing DNA. Of course, I compressed almost a decade's worth of work into that sentence. So tell us about Ultima. Tell us about the instrument. Kind of what's the mission and ambition of you and your company?
The basic premise beyond Ultima is that biology has essentially a source code, DNA. All biological information is stored in DNA. That DNA becomes RNA, becomes proteins, but the source code is DNA. And that's true for any living organism. So if you really want to make progress in anything related to healthcare, biotech, drug discovery, so on and so forth, you need to be able to access that code. And that code was historically expensive and difficult to read. And having grown up in the semiconductor industry, my premise was that there's a hyper-elastic demand for more and more genomic information. And if we could bring some of the same beliefs that exist in the semiconductor industry in an everlasting need for more and more data, and some of the methodologies and tools, we could do the same thing for biotech. So Ultima was founded to come up with a very low-cost genome. Genome is a proxy for amount of genomic information you read. We came out a couple of years ago with an announcement of $100 genome, which was kind of a transformative price point at the time. But we also promised to keep it going, not to stop. So even last week, we just reduced the price to $80 a genome. And we promised to do this for years and decades to come. So the idea is to create a Moore's law-like dynamic for biological information with our first tool, the UG100, which is the $100 genome.
It's interesting because Illumina, the market leader, everybody in the genome space knows Illumina, for a long time seemed to be following that recipe. They made this Alexa acquisition. They drove down price. They got to around $1,000, and then they seemed to kind of be like, okay, that's enough. I think the interpretation of their business strategy was, well, once you get to a certain price point, then you can price in diagnostics and payers will underwrite. And so if you cut prices anymore, you're just cutting into your own margin. You're not unlocking more markets. Is there counter evidence against that? How do you think about kind of like that pricing dynamic and their business strategy relative to what Ultima is going after?
So, when people drive their costs down or price down, it's a function of two things. It's their cost. Can they keep driving down their costs or up their scale for a given cost? And their belief in the elasticity or hyper-elasticity of the market. So we differ in two ways. One is we came to this with a radically different architecture. We could spend time talking about it later, but it's a radically different architecture, enable us to keep marching down the cost curve. The second one is we are complete believers in the hyper-elasticity because you're not making a fixed commodity here. You're not making a chair that if you made chairs 10 times cheaper, people wouldn't sit 10 times as much, right? You're not making even food. It was 3 times cheap. People wouldn't eat 4 times more food. You're making a commodity which is data, and data and IT computers have shown us for decades that every time you make it twice as cheap, people consume 3 times as much, right? People talk about Moore's law as the driving force that people march to. But then, there's Jevons paradox, right? Every time something is twice as cheap, the consumption does not stay flat. It actually goes by more than twice. So you consume more of that thing. So we believe in that. Now, why? Because the human genome is a test and is an important test. But even today, a small fraction of people have had their genome sequenced. Most of the time, when you hear people go for genomic screening, which is also rare by itself, it's not the whole genome because it was not affordable. So people have compromised on how much data. So even for the reimbursed medical test, people do not collect all the information they should be collecting because of price. And then there's many other drivers of hyperelasticity. There's everything happening in the AI space, in bio meets AI at the cellular biology level, understanding the basic cell. And then there's everything happening in the cancer space, when it's no longer about my single inherited genome that's averaged across my body, but it's that bloodstream where you have shreds from about 10,000 worth genomes equivalent from cells dying across my body, and you want to read my genome thousands and tens of thousands of times. So it's not that I need a human genome and 100 is good enough and 70 doesn't help. I need 10,000 copies of my genome. So there's years and decades of progress that needs to be made here.
Yeah, I mean, Gilad, I think we at ARC, we truly believe that biology is the truly ultimate big data science, and kind of enabling technologies that allow us to read that information are going to be kind of, making big wins. And so, but maybe just to kind of go back and talk first for our audience a bit more on the technology side. And if you can just kind of explain to us and the audience, how is your technology architecture different than Illumina? And basically on the side, how are you enabling that kind of cost reductions at the moment, and then for the kind of going to the future as well?
When you want to get more information content from a certain unit area, and the sequencer, what a genomic sequencer does, it takes DNA in one way or another, it puts it on the surface, and it reads it out by various mechanisms for making it visible, and you can see it. Now, in the semiconductor world, in the computer world, when you wanted to put more and more transistors, more and more compute power per unit area, you kept shrinking the transistors. And you did that by printing them first with visible light, and then you went to UV light, and then you went to deep UV light, and today it's extreme UV, 30 nanometers, and you've really shrunk the size of those transistors so you can fit more and more in a given chip. In DNA, you can do some of that move, but you can't really do all that because DNA is sensitive to UV, and the deeper you go into UV, the more sensitive it is, so it gets damaged. So the classic playbook of semiconductor, which is let me just shrink, doesn't fully work here. It works to some limit, but then hits a wall. And if you look at what our competitors did, they kind of got very close to that wall. And when you get close to the wall, you really slow down. Our approach was, let's take the other direction, which is let's make the substrate that we're looking at much lower cost. So we talked about semiconductor world where Moore's law has been all about shrinking and increasing speeds. If you look at televisions, for example, flat panel televisions, our eyes have not gotten better over the last few decades, and the pixels have not really gotten smaller. What happened was the manufacturing techniques for making those televisions have gotten to larger and larger sizes. Today, the screen of the computer or laptop you're looking at was probably made on a 3 by 3 meter piece of glass or a 10 by 10 meter piece of glass. So scaling came and cost reduction came that way. Our approach was that because DNA has a finite density, while you can see it optically, because you don't want to go UV, we will increase the substrate very cost efficiently. So instead of the traditional flow cell, which is made from highly specialized glass, going through many, many complex processes, we went to a large substrate. It'd be a very, very simple substrate. And we piggybacked on the semiconductor industry. We literally use a 200 millimeter 8-inch silicon wafer as our flow cell. There is all the flow cell with the connections and hookups and the processing and the patterning. None of that exists. It's just a large, highly flat, highly efficient surface. But because the semiconductor industry makes hundreds of millions a year, it costs very, very little. So we took that approach. And that is the major. And then, of course, we used a very low-cost chemistry with a lot of machine learning, AI techniques to get the signal from that very low chemistry. So it's a path which was designed to not waste anything physical, be very, very frugal, leave the work up to your signal processing, and get to a path that lets you go for cost reduction for years to come.
I'm going to try to simply summarize how I understand like an Illumina system works, and then maybe you can offer the comparable summary for how you. So Illumina, I take DNA, I chop it into little chunks. I probably amplify some of it. I flow it across a flow cell, which is, like you said, like an intricately carved piece of glass that has little things that grab onto the ends of the DNA, the little chunks of DNA. So then I have a little DNA forest. And then maybe it grabs on both ends, and then I need to amplify little clusters of it. So I end up with like a forest with single species of DNA growing up in clusters. Then I do something where it like rips it apart into single strands that are sticking up like a forest again. And then one by one, I flood the system with kind of little nucleotides that are going to little letters that are going to attach on the opposite letters and flash a flashlight in those little clusters. And each time I'm taking a high definition photograph of that forest and being like, okay, those are A's and those are B's and those are C's. And I do that one by one by one by one, stacking up. And so I get the kind of a recipe for each strand. Okay. So that's my understanding of the Illumina system. I probably botched some of it. Okay. What does the Ultima system do? And kind of the same, simple, my 11-year-old could get it.
So at a fundamental level, it's still the same premise. Your 3 billion long piece of DNA, you don't look at it that way. It's chopped up into little pieces, different ways to do it, but the pieces are several hundred long. And each one of them becomes a colony or a cluster, multiple copies of the same species. And you're reading them base by base until you finish the whole thing. And you're doing this with a very, very fast fluorescent microscope. So like a microscope, but dramatically faster. Where we differ is that the substrate we're putting the DNA on is not a patterned flow cell sandwiched between two very specialized, very accurate pieces of glass. In our case, the colonies of DNA are just spread out across an 8-inch, 200 millimeter silicon surface. And there's no channels, no connections, no classical way to drive the liquids to. And the way we get the liquids to them, because there's no connections, is we literally drizzle the liquid from the top in the middle and spin. So technology we borrowed from the semiconductor industry, where it's been used for many, many decades. Every chip in your computer or iPhone or whatever has gone through tens and tens of these steps. It's called spin coating. It's a very fast, efficient, uniform way to get your liquid onto your surface without having to do anything to your surface, patterning and so forth. So we still have a large area. We still have many, many species, as you call them. We still image them, but we do this on a much larger surface, in a much more fluidic, efficient way. And then there's another layer of complexity, if you want to go into that where there are others, every time they let one base, they march forward by one base, and they ask the question, which base is it? Is it an A, C, G, or T, the four possibilities? We do something a little bit different. We flow only one base, say only T. And we ask a different question. we ask how many T's went in. We know it's a T because nothing else was added. We just don't know if it's 1 T or maybe 0 T or maybe 7 T's. And that behavior, that choice, gives us two huge advantages. One, we're much more efficient in the way we use our enzymes. We don't have to replenish them, which is the more expensive of the things you flow. And B, we are extremely sensitive for base substitutions. For us to make a mistake, to say the T, let's say the tumor, then we'll talk about use case in a second, but let's say your body should have an A in that location. But the cancer that started growing, the tumor had a T. And now you're looking at the blood and you're saying, is the tumor back? So you look at 10,000, 50,000 sites of the same location, and you say, are all 50,000 A's or is one a T? And you really, really want to make sure your tool doesn't tell you, hey, once in a while, it makes a mistake. In our case, because of the flow-based chemistry, you have to make several errors to make a mistake. Because an A has to not be an A and a T has to be a T, and it gets more nuanced than that. So we really make very few base substitutions error, which is in one of the prime use cases which needs more and more sequencing, which is looking for cancer, is incredibly important. To be accurate to what's called SNPs or SNVs, single nucleotide variations, which are the main difference between genomes, especially when you talk about the world of cancer.
So you wash it with one letter, and then do you wash it with another letter, and you do them?
Yeah, you cyclically go through your alphabet, but you have a 4-base alphabet, and you cyclically go through it, and you march along. So if that location had no A and you flowed an A, it'll stand, and if you flow a C next time, it'll progress by the rate, which has to do with what you're flowing versus what the sequence at that location is.
And how do you judge how many of a letter in a row you have?
So that's where having a very, very highly accurate optical system with a very stable laser enables you to essentially, it's a dynamic range. You're looking at gray levels. You're saying that's a 7, but that's an 8. So that could have been harder to do with older cameras and not as stable lasers and less advanced image processing. But these days, it's pretty straightforward to say that's an 8 and that's a 9.
Got it. And has that improved? I mean, it seems like that's tractable with machine learning to some degree. Is that a vector of improvement in terms of reading those, call it homopolymers or same letters in a row?
Yeah. So when you make the architectural choice we made on the chemistry, it's obvious that you're going to be very good at base substitutions. And those are like 93% of the occurring variants. And your challenge is how do you deal with the homopolymers once they get long? Once you have 70, 80, 90, 10T. And when we first stored our initial data, our accuracy for what's called variant calling accuracy, or indel-F1 is the technical term, for insertions and deletions, when things get longer and shorter, was like 95%. And now it got 98, and now we're 99.66, which is kind of like world class. So on the variants, on the insertions, deletions, when things get longer and shorter, base substitutions were extremely accurate. And we can go back to that later, but we have this mode, PPM-seq mode, where we're better than 1 in a million errors, which is critical for oncology. We can talk about that in a second.
So follow-up question for me here is that, you came out with a $100 genome, now it's 80 already. How much of that kind of simple surface and actually being kind of able to go, further in shrinking in actually kind of making that more dense that surface can kind of lead you to maybe a $10 genome in number of years? Or do you think it needs more of the kind of different hardware updates, chemistry updates?
So the move we made from 100 to 80 came also with increasing the system's output by about 50%. Like how many billions of reads per or terabases you get per run. And that happened on the same tool. So we took the tool we released, commercially released a year ago, and a year later we said, here's an upgrade that involves some of the process, some of the chemistry, some of the image processing, but it's the same tool we sold you now. Is a better tool. You don't have to replace tool. And there's a series of steps planned out for the next few years, which can't obviously share all of them, which count on chemistry process changes on the same tools and generations of tools together to keep marching down that cost curve. So if you look at all the levers you have, all the degrees of freedom you have from the first generation, which is where we really were a year ago, there's multiple steps to take. So a lot of runway.
Yeah, of course. But you do see possible $10 genome.
I think the $10 genome is not a question of if, it's a question of when. And both in terms of the ability to do it and in terms of having the hyperelastic demand that when the world is a $10 genome, a lot more will be spent on sequencing than it is today.
Well, that's a good segue into that application space. Why don't you talk about some of, I mean, you've had some application wins. One, I think it's worth like just stepping back for a moment. And Ultima was started in what, 2016?
The very end, yeah, beginning of 17, end of 16, yeah.
Okay, so this was a, 9-year journey basically to get an instrument to market that has a radically inexpensive genome. And so like that deserves in and of itself, like congratulations, like what a kind of push, to get there. And you're selling into end customers now, which is like, I mean, it's super against call it a single monopolistic competitor.
Not only that, Brad, look at the Roche. Roche, that big company, took them 10 years to come up with the instrument and they're still not selling.
It's true.
And so much more money, how many FTEs, right? So this is it's a really accomplishment.
Yeah, I think it took us about 7 years from the day we started till commercial release, a little bit less than that for early access. And it's a complex instrument. If you visited or seen, it's a lot going on there because you're not only developing an ultra high throughput imaging instrument, which is what I did back in the semiconductor industry and others have done. You're doing that, but at the same time, you're doing your own molecular biology and developing your own enzymes, and developing your own chemistry, your own analogs. So it's very extremely cross-disciplinary. You're really vertically integrated, and since you do everything pretty much from raw materials across the whole chain, which makes it a lot of work to come up with the first instruments. But once the flywheel is going, it's really fun to see it. The 1 year from within 1 year we boosted our output by 50%, right? And but it took us multiple years to get to the first point and to get the teams in place and the architecture in place and so forth. But your question about so now last year has been good because we have validation. We've had several things recently that have validated that we are where we want to be. We got selected by a pharmaceutical consortium of 14 pharma companies, most of them the largest pharma companies out there, several larger, smaller companies, and they chose to they took the UK Biobank, which is 600,000 samples collected across the UK with connection to the medical files, and have already been sequenced. The genomes of those have been read before us by the other company, but they wanted to add proteins. And proteins, you need to tag them, which is a different technology. In this case, a company called Olink came up with the technology of how to identify the proteins, a company now acquired by Thermo Fisher. But after they tag them, you still need to read DNA. DNA here is really a barcode. It tells you which protein, which antibody connected to which. In this case, we got selected in UK Biobank, which was really 14 rather conservative companies, a very prestigious site, very extremely competitive. Comparison between us and Illumina, we had to prove all the full technical compatibility, the ability to run at the scale. So that was a very, very important win.
And that's interesting because it's kind of like there's probably a high degree of sensitivity to a substitution error, right? Because like if you get the barcode wrong, like you're reading the wrong protein. And in protein space, you're looking for like the needle in a haystack, right? You need to get to very kind of like low concentration kind of reads.
Also, I think it's very interesting that you beat Illumina, given that Illumina has a SomaScan on their NGS readout as an assay.
I think it was a very interesting competitive dynamic. And I think, accuracy mattered, cost mattered, and understanding of those pharmaceutical companies that the competitive dynamic is good for everyone. And I think all those things played a role. But it was a validation of being ready for prime time. And then with that, if you attend the AGBT, the conference in our industry last week, suddenly there's a network of service providers. So we had the tool, and our tool was used by some for-profit companies in a more stealthy mode where they're developing, let's say, a new cancer assay with us, and some large genome centers like the Broad, which was our first customer and our first partner, and others like that. Now we have service providers. So now folks that don't need an ultra high throughput sequencer, that don't need to do tens of thousands of genomes a year, have access to our technology. And the service providers typically will only adopt the platform if it meets two criteria. One is it's ready for prime time, they can actually run it. They're not, they don't have a scientific mandate to explore new technologies. They have a mandate to make money by selling sequencing services. And two is that they have demand for it. So I think having a network of service providers, which we just announced a couple of weeks ago or last week, is another very strong side of validation. And the third recent event was momentum in the really the AI meets bio moment of understanding how cells work, and that's worth a longer discussion. But the Chen Zuckerberg initiative just announced this billion cell projects. And a billion cell, for context, the world, in terms of sequencing the genomes or the transcriptomes, the RNA of single cell, there was a very impressive human cell atlas project that ran over about a decade and achieved close to 100 million cells. This project that was announced is a billion cells that are going to be sequenced with our technology. A few weeks before that, a therapeutic startup called Viva Therapeutics, together with NVIDIA, announced that they're putting out a data set of 100 million cells, which were perturbed, were chemically disturbed. The RNA was read to use that to build a machine learning model of how cells behave when you perturb them. In their case, to understand how you go from a healthy state to a cancer state and back. And we did the sequencing on that. So finally, we're doing extremely large-scale sequencing in that kind of bio-AI moment in the single-cell space.
Great. Maybe I actually have a follow-up question. So I think I mentioned this to you. I did my PhD with Aviv, so I spent a lot of time in the single-cell space. And we've seen your stuff with Parse, with Scale Bio announcement, which was also with CZI, and then now the billion cell with kind of 10x Genomics. How do you think, we see this as just like, this is not going to be like 1 billion cell project and that's it. We just see this as like, there was a one first human genome and then we realized that we need many more. How do you see this space kind of growing in the future, in the drug, not only in academia, but in the drug discovery? Like, could we envision the future where like 1 billion cell projects are the kind of norm to build the foundational models?
First of all, just to frame things, right? Cells are incredibly complex, right? If when you try and understand a basic atom, hydrogen atom, you do it with a pen and paper, right? And then more complex things, you use advanced math models. When you go to the protein, you needed AI, right? And that's all the AlphaFold moment and the Nobel Prizes this year. A cell is another layer of complexity far above that. And, you study biology, I study physics, cells are hard to understand. And we've been at it for God knows how many years, and there's no fundamental model. There's many, many edge cases. Cells are so many different things in different environments. So we're so far away from having any basic analytical model of how a cell works. And I think there's a general consensus out there that this is sort of the classical AI moment. AI is the way to understand how cells work. And understand how cells work is because I'm curious, because I want to understand science, but or because I'm developing a drug and I want to know which drug works. I want to know how aging works. I want to know everything. Cells are the unit of life. And we're so far away from understanding it. So how many cells do you need to measure to develop a machine learning model? For what? For a specific question, does this cancer drug work or not? Or how should I tweak this molecule to make the cancer drug better? Or generally understand everything? Nobody knows, just like, the ChatGPT moment where ChatGPT 1 wasn't good enough and 2 wasn't good enough and 3 was the wow moment. And 3 trained on, you probably know better than me, but on the entire internet, that many trillions of tokens. What's the number in the cellular world? It's not language, it's something else. So people make analogies, but the analogies are very partial. No one knows. Intuitively, we're just beginning to tickle. It's this it'll go through phases. The billion cells will definitely have scientific value, but it'll work for one type of, limited type of cells in limited scenarios, and it'll start providing value. And then there'll be larger ones, and there'll be specific ones. And pharmaceutical companies will not share their experience with other companies. There'll be some open source. So hard to predict. Nobody can predict the specifics, how this race or how this world will. But between us and the moment where the cell is truly understood and truly, you can program it, I think we're orders of magnitude data still to go, but nobody can prove that at this point.
Yeah, I think you can safely say we don't have enough data. And that's like the story of biology for, forever. But even the Human Genome Project, when I think that, the results of that were in some ways disappointing in that we sequenced the genome and then we didn't get like all these hereditary diseases that we didn't know, like popping out. It's like, oh, this is how, because you're just getting the recipe, you're not getting the expression, it differs cell by cell. There's so many layers of complexity in biological information unpacking.
And actually, Jens was recently saying the protein was understood that many years ago, and it'll take that, he said 6 years. I think he's a bit optimistic here, from the protein to the cell. But once you have the cell, it's from the cell to the organ and from the organ to the body. But there's obviously a lot of work to be done here. The example you gave is also interesting because if I sequence one person, which was what was done 20 years ago, and I have that one person's medical file, and that person is tall or bold or had this disease or did get cancer or didn't get cancer, what do I do with that? There's 3 billion letters. 30, 60 million of those are coding, but the other ones are clearly influencing as well. And what's the point of sequencing one? There's almost like very little value in sequencing one person. The value is, do you need 1 million people with their medical files and their 3 billion letters? Or do you need 100 million people with their medical files and their so the AI needs training sets, right? And the ChatGPT moment was very convenient that all of us wrote books and blogged and sent emails and whatever, and everything humanity has ever written was used to train that thing. In biology, what are you going to do? You need to create the data set. And there's some interesting analogies of here of like, okay, maybe take a different field where AI is having a role, self-driving, right? You can have a Waymo approach, which says, I'm going to, put those cars, drive God knows how many millions of miles in San Francisco, record every inch of sidewalk, train, and then have a self-driving taxi, which they have now. Or you can take the Tesla approach, which is I'll sell you a car, you'll pay me, I'll make money, and I'll use your data to train. So that's more like a ChatGPT. ChatGPT didn't have to pay for the internet being collected. We did it on our own. They came and took the data. The Tesla moment is more like that. Those cars are driving around, you're collecting the data. I think here it's going to be a combination of both. People will want to be tested for inherited cancer risk, for ancestry, for some condition that's not understood well. So people get sequenced all the time. If you do whole genome sequencing for those people, instead of just looking at a narrow panel, you're creating a great training set. And you're being paid because there was a reason, there was a medical reimbursement for that test, but you're creating a training set. Same thing is even more true in cancer. Every time someone has a cancer, and we can talk about MRD in a second, but you test for residual disease. If you do the test properly and you actually collect all the information, you're creating a training set for detection of cancer. Single cell world is a bit different. You have to go harvest the data. That's more of a Waymo moment. You've got to invest.
Well, it's only a bit different because as of now, like you can imagine a future space in which if you have a good single cell model, actually, sequencing, doing a single cell sequencing of your own cancer is an obvious example, right? Where it's like you have different cancer populations, but that'll be more informative than it was in the past. And so then people will go after that diagnostically, that then will improve the models they're built on top of.
For sure. And when a pharmaceutical company will do a large lab in the loop, as Aviv calls it, and do a big experiment because they're trying to work on a specific drug, because they're getting paid for that drug, that data set, that learning will be used more broadly. So the more data gets collected, the stronger the models get, the more they use, and so forth. It's a virtuous cycle, and everything has to do with AI, and specifically in biology.
And for Ultima, how important is it for you to get into kind of like the diagnostic space as opposed to just living in the research space? And then how do you even do that? How do you penetrate that? You talk about MRD if you want, but like, what is the playbook to get there?
So if I look at our early adopters, just ballpark a 50-50 split between research customers and diagnostics customers. So from day one, very, very early, as soon as we started shipping early access tools, we had traction with diagnostics company because there's many, and over time you'll see DNA diagnostics for all sorts of disease, neurodegenerative disease, heart conditions, but the immediate poster child is cancer. Cancer is the classical genomic alteration disease. What's happening now, and you're probably following the space, is this huge success in MRD, minimal residual disease. which is someone had a tumor. The tumor was usually treated or taken out. You compare the tumor to the normal, you see, well, that tumor was different than the rest of the body by a set of mutations. And if those set of mutations appear again in the bloodstream, it's a sign that the tumor has not fully gone away or has come back. Cancer recurrence or residual disease, different terminology used here. So what characterizes those applications is that you need to see a lot of DNA. I'm not reading what you inherited from your parents, which is that I take a cheek swab or white blood cells or whatever I want. I take any cells from you, I read, I do an average, and say, on the average, you are you. This is very different. On the average, you are you, but maybe 1 in 100,000 of the molecules of the oligos floating on in your bloodstream is from a tumor. Some are from your liver, and some from your heart, and some from your lung, and some from everywhere, but there's one from your tumor, so that tumor's back. So that needs extremely high. You need 3 things. It's simplistically, it's a classical needle in a haystack problem. I got a lot of hay, but I got one needle that I need to know if that needle is there. So you need to be able to read a lot. So you need to be very efficient how you treat the DNA, which we are extremely with this mode, PPM-seq mode. B, you have to trust that you saw, hey, a million times, a needle once. You need to know that it's not a false call. And 3, you need to be able to afford it, because I need to be able to read a lot of DNA affordably and accurately. And that moment that's happening, you've seen the MRD test. Natera is doing incredibly well there. You've seen go from nothing to a very large number of tests. You see other players coming into that space, and the MRD space is not a once and done. Someone has a tumor, you sequence a tumor, and you guide therapy, which is also incredibly important as happening over the last few years. This is a repetitive test. That the person had tumor during treatment, after treatment, years later for recurrence. It's an ongoing test. But whoever creates a large enough data set administering that test and getting paid for that test has a very good chance of being the winner in screening, because they'll have the data set to train to see, well, now I no longer know about your specific tumor, but I have a measurement of the tumor in blood. And if I have that over a large enough population, I have the ideal training set for developing a screening algorithm.
Yeah, maybe for me, when I think about MRD and kind of cancer testing, but also the single cell kind of space, where I think that, this is ultimate big data, is that, biology happens over the time. And every time we do the sequencing, we're doing a snapshot, and so actually this longitudinal sampling and doing the sequencing is going to be the key. And we can see that with MRD. Like, we are excited for MRD because sure, it's helping with relapse and everything, but you'll actually be able to study tumor evolution and have much better precision therapies over the time. And then you can kind of use for other stuff. And I feel the same for the kind of single cell and the perturbations for the drug discovery. It's going to be many of them. And what adds this additional kind of layer of the need for the data is this longitudinal temporal kind of component. How do you think about that side?
I fully agree. I think when you started with saying, okay, $100 genome, what's the point of a $10 genome? At what point is enough? And you say, well, whatever, there's 140 million babies born a year in the world, sequence them all. Okay, mission accomplished. $100, $10, good enough, right? But that's a static genome. But the genome is not static. Again, you inherited a genome from your parents, but now you've duplicated it again and again, and you have tens of billions of cells, right? You have tens of billions of cells. They should nominally all be the same, but they're not. Every cell division is errors. Every exposure to radiation is errors. We are walking errors, right? We have tens of trillions of cells, each one on the average with thousands of mutations, most of them harmless. Once in a while, one of them is very harmful, right? Cancer. But we are walking errors. B, we're evolving, and it gets more complex than that. Our DNA mutates, but our DNA has the epigenomic. How it's folded, how it's accessible, what parts of it can become protein, what's called epigenetic, methylated, how it folds around the histones. All those things are dynamic. So your DNA is not static, not in a single cell, and definitely not in tens of trillions of cells. So if you look at, really simplistically, take a blood draw from any of us, any given point. Once we've created the training sets, every health conditions will have a manifestation of that. Again, cancer, obviously, but neurodegenerative, heart, anything, unless you stub your toe in the door a minute earlier, there will be a sign of whatever is hurting you in your bloodstream in the DNA. And that's premise why we're in early days of years and decades. We're so far away from being digital. Healthcare is so far away from being able to truly understand us. And it's hard to see in one thread how it happens. It's many, many steps. It's the single cell work. It's the population genomics work. It's the MRD cancer work. All of those together are building one common understanding. And I think that's why it's almost like being in semiconductors in 1970. You don't know exactly how it's going to play out, but you know it's going to be exciting.
As someone, like, it seems like a very difficult strategic environment to operate in. You have capital to allocate. You can be building a new instrument. Maybe it has like a bigger wafer or, some way to drive down costs. You can be building like specific kits for different kinds of tests, like for RNA and stuff like that. You can be just trying to like improve chemistry to like lower the cost of DNA. How do you think about those buckets of where you allocate resources? And, it's an industry that's actually been really protected from disruption, I think, for a lot of reasons. There's third-party payers, there's like diagnostic companies are by their nature conservative. Once you qualify a test, you don't want to change how you're doing things. Like there's all kinds of frictions against early adoption. Like, how do you allocate capital and think about the strategic landscape for Ultima?
So we made a decision early on in simple terms to stay in our swim lane, that we are sequencers and we will do one thing as well as we can, which is to keep making sequencing better and drive down the cost of sequencing, drive up the scale. And so, of course, there's always R&D decisions. You do this generation or skip one and go for the bigger one. Invest more in the chemistry, invest more in molecular biology, or invest more in the mechanic. There's always R&D trade-offs that everybody who's ever managed research and development programs managed. But they're fairly basic. We know we're in our lane. We made the conscientious decision early on that we do not compete with our customers. We do not develop kits. We do not develop tests. We partner. And so if you look at our current competitor, Illumina, and maybe potential future competitor, Roche, it's more complex stories over there. And there's decisions to give a whole ecosystem. I will give you a sequencer, but I will also give you long reads, and I'll also give you single cell, and I'll give you a solution. And for some customers, that may be great. When you buy a computer for yourself, an Apple is great. It's great that it connects to your phone, your watch, your photos. It's wonderful. When you're AWS and you're building a data center, you don't go to Apple and say, hey, give me computers. You don't even go to anyone else and say, give me computers. You choose the best CPU, the best GPU, the best memory, the best fans for cooling. You optimize the hell out of it. We believe fundamentally that sequencing is a data generation business, and it's not like any other classical diagnostics tool at the doctor's office. DNA is the easiest thing to put in a tube and send away. It's all about efficiency of generating the data. And when we made sure we really, really stay in our lane, we focus on the data and we partner. You mentioned sparse, scale, and 10x. We want the experience to be really easy to work. I choose the 10x 3', but I will work with you guys on the sequencing. And I choose the tertiary analysis from this company, but I will work with you. And I want the library prep for NEB or IDT or Watchmaker or whatever. I will choose. We are very, very focused on doing one thing and collaborating with our entire ecosystem, letting our customers, which are usually the advanced customers, kind of build the best of breed solutions. So that was a long answer for that. Our decisions are pretty straightforward. We know exactly who we are and what we want to be, and we just have to kind of plow ahead.
How do you think generally about the space, right? If the thesis is that kind of, the data is the way to go, and, this is ultimate big data science, I could definitely see that there are multiple, kind of winners in the space, not like a single winner, like how it was until now with Illumina only kind of, having a monopoly. I think actually it was really not great for the market. And, now just like Roche coming out, there is also Element and something that kind of lower throughput. How do you see this space in like 5 years or even longer kind of period? Are multiple kind of players coexisting together and offering their products? And it's like Microsoft, Apple, kind of dichotomy.
The space is growing, right? And will grow meaningfully. This year we disrupted and helped cause an average cost drop in the field. And I think Illumina even said now that between 25 and 40% bit growth this year, right? So no top line dollar growth, but no fall either. And 25 to 40% growth in the underlying demand for data. And this is just the beginning. So we've got years and decades of that to come. And so the space will grow. we know exactly where we want to be in this space, which is the data generation players, the AWSs and Google Clouds, and we want to be the data generation engine of this industry, which we think is crucial for everything has to do with oncology, everything to do with this very, very large single cell experiments and large population studies. There are many, many, many other use cases. There's rapid response to newborns, distributed infectious disease. There's so many, many, many cases for sequencing to play a role. So again, whether 7 years from now we're GPU and they're the CPU, and who's going to win which segment and which is the biggest, I obviously believe the segment we're going for is going to be the biggest, and I believe we're going to lead in the high throughput sequencing because we've got the architecture. First of all, we've got the team and the architecture. B, because we have a single-minded focus on it, and we believe this is going to be the biggest market. And if I can't prove that to you, I'm sure that it's going to be a very big market.
Yeah. And just on the architectural choice, though, you would always sit in that high throughput space, right? Like you have these giant disks. You're not going to have those like sitting next to a doctor, right? I mean, it's basically like a...
So I don't know if you remember, but many, many years ago, right after the Walkman, there was the Discman, right? People walked around with something that, not much larger than, like, let's say 2 iPhones, but carried around the disc. That was a 5-inch, whatever it was. The fact that we have the disk does not mean we cannot make small benchtop systems. And many things in our architecture can't scale down. So when we feel we have the need to, and I said it's a data generation industry, but it's related to healthcare, and some countries don't let you send out, and some things are more distributed. There are reasons why not all the sequencing will go to the ultra-high scale. Our architecture can go in that direction. Right now, we're very focused on our main market, which is the high-throughput market.
Got it. Okay, well, Gilad, I really appreciate you taking the time. Ultima is such a fascinating company. I find this space to be so fascinating, in part because there's so many, it is clearly growing very big, very quickly, and it is so clearly very early. You mentioned UK Biobank, 600,000 people. Like that is, there's millions of babies born a year, whose DNA we probably should be sequencing, as soon as possible.
I think there's only one end game here, right? Which is X years from now, and none of us knows when that X is. It's 5, 7, 10, 12, but everyone gets sequenced every year, or every time you go to the doctor, right? They check your cholesterol, they check your white blood cells, they take whatever. There's no way they don't check your circulating DNA. There's just no way. What none of us know, and you guys are investors, I'm in technology, but none of us know when is that happening, what are the steps for that happening. But there's only one obvious end game here. So this is early days.
Yeah. And it's kind of so Llama 3 or, one of these large AI models, they're trained on, call it 15 trillion tokens. The UK Biobank has, depending on how you embed the DNA, 400 trillion tokens sitting in its database. We just, the space, the solution space is so complex, or the embedding space is so complex. We actually need even more data, and it's a sign of kind of how early we are in beginning to apply AI to these data sets.
Yeah. If you look at how much of the GPUs in the world that NVIDIA sells today are cranking out finding new bitcoins or training large language models versus actually being used for biology, I mean, they have been doing amazing work in this space, and they're focused on it. I bet you it's still a tiny percent of the GPU power in the world is being used to healthcare, but 20% of the US GDP is healthcare, and the importance of healthcare. So I think we can safely wager that if you wait a few years down the road, if you look at what percent of GPU power goes to using that data you just mentioned, it's much, much larger than it is today.
Yeah, for sure. Well, I really appreciate you coming on the pod, and we enjoyed having you. And we wish the best for Ultima, and hope that you, sequence a lot of $80 and declining in cost genomes.
Thanks. Really, really enjoyed this. Really appreciate it.
Thank you for joining FYI, the For Your Innovation podcast. Please make sure you subscribe on whatever podcasting platform you adhere to. I thought it was a fascinating conversation with Gilad, and I thought his point that more and more GPU power as a share is probably going to be devoted to the biological space as is probably true. And in part because as at ARC, we expect macroeconomic growth to inflect meaningfully over the latter half of this decade because of the acceleration that disruptive technologies offer, where you will have performant robots manufacturing things more quickly, AI, supercharging the productivity of knowledge workers. What does that leave to spend money on? In a world of abundance, where do we throw our resources? And it's increasingly clear, as you can see from the ultra wealthy, that people will throw their resources at trying to live forever. And so there will be kind of a lot of demand to invest in technologies that can cure and diseases and make life longer. And I think there's going to be a high ROI in devoting compute and AI resource to understanding, these incredibly complex biological systems that, comprise us. And so I think that there's, it's clear that we are so very early in this space. And I do believe in Ultima's position that there is wild demand elasticity as you go down a price curve of being able to generate biological information. So it should be interesting to see how a space that was following a steep cost decline got to around $1,000 a genome in 2016 and somewhat plateaued, how that's going to respond as prices decline again. How demand is going to respond and how the application space is going to expand when you have, much larger volumes of information available for a relatively inexpensive cost. Thank you for joining, and we'll see you next week.
ARC believes that the information presented is accurate and was obtained from sources that ARC believes to be reliable. However, ARC does not guarantee the accuracy or completeness of any information, and such information may be subject to change without notice from ARC. Historical results are not indications of future results. Certain of the statements contained in this podcast may be statements of future expectations and other forward-looking statements that are based on ARC's current views and assumptions, and involve known and unknown risks and uncertainties that could cause actual results, performance, or events to differ materially from those expressed or implied in such statements.